Hi everyone, I think I'm live. So let me see if I can hear myself. Let me quickly check if I can hear myself. Yep, I can hear myself. So hi and welcome to another class. So today we'll be again solving two problems. Now today's agenda will be mostly around trees. So we'll be solving problems on trees. Uh, we'll be solving two problems, one easy and another hard problem, and then I'll be giving you some questions for homework as well. Now coming to like what the agenda is, like what we are doing exactly here is that I'm running a series where I'll be solving problems like every Monday, Wednesday, Friday, two problems every day and a few problems for your homework. The idea being that within the end of 29 days you will have a lot of problems. You would have solved a lot of problems and you would also have gained some pace, so you can continue solving more problems, right? So let's get started with today's problems. So the first problem we'll solve today is a easy problem. It is inserting a node in a binary search tree or a BST. So we are given a BST and a key k. If k is not present in the BST, insert a new node with the value equal to k into the BST. If k is already present in the BST, do not modify the BST. So we have 213 and k is 4. Then we should insert 4 in its actual place in the BST, right? So that's about, because 4 is not there, and 1 2 3 6, and after this if you place 4, so 4 should be inserted in such a way that the resultant becomes 1 2 3 4 6, right? So yeah, like let's understand this, like how the insertion would work. So 213, we have 2 1 3, and we are inserting 4, right? So what do? We start from the root node. Now what is the property of a binary search tree? The property of a binary search tree is that if a key, like how do we insert in the BST, or what is the property that BST follows? All the keys on the left hand side or the left subtree of the given node will be, the value will be less than the given node, right? All the values in the left subtree, all the values in the right subtree should be greater than the given node value. So this is a BST till now. Now which side, for this root node 2, which side will 4 belong to? 4 will belong to the right side, so we will shift to the right child. Okay, here. Now 3, 3 is there, it is not equals to 4, so 4 will belong to which side of 3? Left or right? Right side. But right side child is not there, so we will just insert 4 in this place, right? We will just insert 4 in this place. So that's basically like the idea here. Let's take the example of 1 2 3 6. So 1 2 3 6, and here we are inserting 4, right? Here we are inserting 4. So 2, which side will 4 belong to? Right side, will go right side. 3, which side will 4 belong to? Right side, so we'll go to right side. For 6, which side will 4 belong to? It will belong to the left side, because the left side will have value smaller than 6, so it will belong to the left side, right? So we'll add 4 here. So this is the idea for insertion of node in a BST. Now, how do we solve this problem? We'll create a helper function. Let's call this is BST, or create add to BST. Add to BST. We have some current node. We are at some current node, and we have a value k, that is we are inserting, right? K is something we are inserting. Now condition is, if current node equals to null, that is we have reached a null place. So whenever we reach a null place, that means this is where the node should be inserted. So this also should return a node type pointer, right? Add to BST should return a node type pointer. So in this case, whenever we reach a null pointer, here the node should come in, so we'll return a new node, right? So we'll return a new node with the value of k, right? So if current is null, we'll return a new node with the value of k. Now let's come to the other condition. Now if current of if current of data, let's call it data, if current of data is equals to k, if the current node's value is equals to k, that means k is already present in the binary search tree. So we will do nothing but return current. Why do we return current? That is because this expects to be returning an updated node for the tree, right? This function expects to be returning an updated node for the tree, for the current updated node. So this will not get updated, so we'll just return current. So else if current of data greater than k, in that case what we'll do is current of data is greater than k, right? So k should be on the left hand side, so we'll update the left child. Current of left equals to add to bst current of left and k, and return current again. Similarly, otherwise else it will be less than k, current of data is less than k, so in that case it will be on the right hand side, k will be on the right hand side. So current of right equals to add to bst current of right and k, right, and return current. So this is the code that we'll do. Like, let's see how this works, right? Let's understand how this works. So we'll take the example of, let's say 1 2 3 1 2 3 or 1 2 3 6. Let's take the example of 1 2 3 6 1 2 3 6, and we are inserting 4 to this. So we are inserting 4 to this, right? Okay, let's see. So add to bst will call with 1. Now for 1, which condition is satisfied? This current of data is less than k, that is satisfied, so this else condition will be satisfied. So current of right, the current of right will be equals to add to bst current of right comma k. So current node is 1, right? So once right will be add to bst, the new call will be made add to bst, whatever add to bst on current of right and k is returning, that will be the right, and the left child will remain the same, right? Because we are not modifying the left child, so the left child will remain the same, and we'll call add to bst for the right child. One second. Yes. So we'll add to bst on the right side. Okay. Now for the right child we'll go to add to bst. Right now where will we go? We'll go add to bst 3 comma 4, like the node 3 comma 4, right? Now at 3, which condition is satisfied again? Current of data is less than k, so again we'll call current of right is add to bst current of right comma k. So this will return a new node. So current is returned 3, and 3's right is returned something like add to bst. From here we'll call add to bst current of right, that is 6 comma 4. Now for 6, which condition is satisfied? Equals to is not satisfied, null is not satisfied, current of data is greater than k, this is satisfied, right? So for 6 we return current of left. So 6 left, the left of 6 will be add to bst current of left k. So 6 left, so we'll call add to bst 6 left of 6. Left of 6 is what here? Left of 6 is null, so we'll call null comma k. Now when it is null, it will return a new node with value k, so it will just return 4. Now this returns, we recurse back to 6. Now at 6, this will return what? This will return current. So this will return current here, so it will return current. And where did it return current to? The right of 3. See, when we call this, we did this thing, current of right equals to add to bst current of right, that is where it is, this is where it will be returned to. Now current of right, that is right of 3, will be this new node, right? So right of 3 will be this new node 6 comma 4, 6 and 4 on the left child. Okay, now this also returns current, this also will return current, 3 will also return current. Now where will it return current to? It was called from 1, it was called from 1, so current of write at this position it was called add to bst 3 comma k was called. So once write will be this new node 3, so this new node 3 will become the write of 1, this new node 3 becomes the write of 1. So let's mark it here, becomes the write of 1. So what is the resultant tree that we get? 1 2 3 6 4, right? So we get the expected tree. So let's try to write the code for this. Let me know if you have any doubts here. Let me know if you have any doubts on this. But we'll go to the code, we'll go to writing the code for this. All right, so in fact we can write it in place, but let's actually create a helper method. So I'll go with C++. So node star insert, okay, node star is there only, that's great. So if root equals to null, right, so we will return new node. How does this look like? Node val, so we have a constructor node val, so we can use this, right, we can leverage this. So new node, how to close this? Okay, anyways, let's reload. Okay, explain once again. Okay, I'll explain once again, no worries. All right, let's understand this. Okay, let's do one thing. Let me write the code and then I'll dry run and explain, right? Then I think that will make more sense. So if root equals to null, so basically this tells that what will it return? It will return the updated subtree, right? So if root equals to null, in that place k will be inserted, so we'll return a new node with the value of key, right? So else if root of I think it's data, so root of data is equals to key, in that case we should just return root. Or let's actually explain. I don't think I have a screenshot here, so let's actually explain again. So we have this method called node star insert, and here we take the current node and we insert k to this subtree, right? We insert k to this subtree, we are inserting to the subtree, right? Here initially what we'll call insert with, will insert with the root node and the key k. So we'll insert in the entire tree. Okay, in the subtree of current we'll insert k, right? So what will be the condition? Now the condition is if we reach a null node, that will become our insertion point. So if current equals to null, this is our insertion point. So in this case we'll return a new node. So why are we returning a new node? Because this will be used by the, when we recurse back to the parent node, it will be used as a child node. This will be automatically used. We'll see how. Okay, now otherwise if it is not null, so there are three conditions that can happen between the current node and the data. Either the current node is equals to k, is equals to the key, that means k is already present in the binary search tree or in the subtree. So in this case we should just return current. Else if current of data is greater than k, if current of data is greater than k, what does greater than k mean? Greater than k means our k should be on the left hand side, right? K is smaller, so it should be on the left hand side. So we will update the left child, right? So current of left, this will return the updated left child, is insert. Where will we insert? In the left child, current of left and k, and will return current, will return the updated value of current. Else, so what will be the else condition? First condition was equals to k, otherwise greater than k, else will be less than k. When current of data, when the current data is less than k, that time it should go to the right child. So current of right, we will insert in the right child and updated the updated right child. So current of right comma k and return k. Right, just see how this works. Let's take the example of 1 2 3 6 and we have 4. We are inserting 4. How will this work now? Let's understand this. We will start from the root node. So what we will call is insert root node is 1. I'm writing the data here 1 and it will pass the pointer 1 and k is 4, right? We are inserting 4. So we are calling this now, right? So what is current node? Current node here is 1. The right of 1 is what? It will call insert again with the current of right. So insert, this calls insert. Remember the line where it is calling insert at this line, right? Current of right equals to insert. So insert, this is calling insert for current of right, that is 3 with the value 6. Sorry, with the value 4. 4 is to be inserted, right? Okay. Now for 3. Again, like just treat 3 to be a different node altogether. For 3, again, see all the conditions, none of them will be satisfied. We will go to the else part, right? I'm not sure if I'm lagging. Okay, I'm not. So we will go to the else part, right? Again, so current of right is equals to insert. So right of 3, the right side of 3 will be equals to what? Insert. It will call insert again for the right child. So what is the right child? 6. For 3, the right child is 6 right now. It will call insert 6 and 4. Okay. And remember where it was made the call at this line again, current of right. Okay. Now for 6 comma 4, for 6 comma 4, which is true? Current of data greater than k, this is true because current of data is 6, 6 is greater than k, that is 4. So what will do? Current of left for 6, what will do? Current of left is equals to insert, will again call insert. What? With what? Current of left. What is the left of 6? Left of 6 is null. So we'll call insert null comma 4. Now what is, this is satisfied for null comma 4, this is satisfied, current equals to null. In this we'll return a new node with the value k. So we'll return a new node with the value 4. So now this returns a new node with the value 4. This is returned, right? Where does it? Now it comes back to this insert 6 comma 4. So it will come back to this, the control will come back to this. The control will come back to this. Where does it come back? For 6, remember it called here, right? Current of left equals to insert. This is where it was called. So current of left, the left of 6 will be insert, whatever insert returns for current of left comma k. So what did insert return? It returned the node 4. So current of left, that is the left of 6 will have 4 now. The left of 6 will have 4 now, right? And then return current. So this will be returned to this call. Insert 3 4. So this is done. Insert 6 4 is done. Insert 3 4, this is returned to. Okay. Now for 3 4, insert 3 4, where was the call made? The call was made here in this line. Current of right equals to insert. So insert returns what? 6 4, this one. It returns the subtree this 6 4. Now current of right. What is the current node? 3. 3 is right. The right of 3 will contain whatever has been returned. That is 6 4. So the right of 3 will contain this 6 4. The right of 3 will contain this 6 4 and the left will be unaffected. So the left is anyways not there. Left is not there. So it will be unaffected and we will return this. This will be returned to insert 1 4. Right. This will be returned to insert 1 4. Okay. Now insert 1 4. Where was this called again? This was called in this line again, current of right for 1 4. Insert current of right. So here we call 3 comma 4. Insert 3 comma 4. So it comes back here. So current of right, what is current node? 1. So the right of 1 will be whatever this returns, in this insert call returns. What did this insert call return? This return this one, right? This 3. So it will be current of right will be 3, 6 and 4, and the left will remain unchanged because the left we are not affecting. We are just updating the right child. The left child will remain as is. So what is the left child? The left child will contain okay, I think here 2 was there, sorry, 2, 1. So the left child will be containing 1, it will not get affected, and the right child will be affected. So now we return this node, we return current, we return 2. So finally we get this updated tree with inserted 4, right? So this is how it will work. Is this clear now? It's greater than, so the key is on the left hand side. So root of left equals to insert root of left comma key and return root. Else if root of data, or else only one condition is left, else root of and return root. Okay, so return root. So now this should work. Let me know if you have any doubts. Okay, so this is working fine. So let's submit this. Yep. So this is working correctly. Let me know if you have any doubts with this. All right. How do you think and develop recursive solution in mind? So just think about what is the problem that you need to solve, right? Here we wanted to insert a node into the binary search tree. Now think with respect to a subtree, like you are given a subtree or you are given some node, right? It might not be the root node, it can be any node of the tree, and within that subtree you have to insert k. So how would you do that? So I can clearly see here that either the left child or the right child will be modified, right? Because k will be either on the left side or on the right side. So whatever is modified, I will modify that part, and I will expect that my recursive relation will return that updated part, right? So I will so I'll keep my left child to be same. I'll only update my right child with what? With whatever the recursive function returns. So again, I don't have to then think about how that recursive function will work. I'll just assume that it works and it will return the proper result. Now to get it to work, I'll have to think about the point where it I have to handle the cases, like if it can be either on the left child or on the right child, I'll update accordingly. And when should I insert, when should I create the new node? When I reach a null node, right? When I reach the insertion point, that time I should insert. And what is the insertion point? It should be a null node, because no node should be available at that point where it is inserted. So that's how I came up with this, right? So I think that makes sense. Let me know if it doesn't. So again, like this is a very good problem where we can actually explore more about how can we think recursively, and this is a difficult problem as well, right? So this is a good problem where we can explore more about thinking recursively, and we'll try to think recursively here as well. Okay, let's see. Okay, so this is binary tree to doubly linked list, right? Binary tree to doubly linked list. So we are given a binary tree, convert it to a doubly linked list in place. Okay, so we have to convert in place. What does in place mean? We cannot use additional space, right? We can use recursive space definitely, but we cannot create new nodes. We cannot create new nodes. Whatever we have to do is we have to do within whatever is existing. Whatever are like we have to convert this tree only into a doubly linked list. We will not create a doubly linked list separately. The left and right pointers of the nodes are used as the previous and the next pointers respectively in converted DLL. The order of the DLL must be same as the in order traversal of the binary tree. So the first node is the leftmost node and the head node of the DLL, right? So for example, 25, 12, so this is our binary tree, 10, 12, 15, 25, 30, 36. So it will be converted into a doubly linked list like this: 25, which is the first node that is visited in order, then 12, the second node. In order means left child, node, right child. In order means that one. So then 12, then 30, then the left subtree is completed, then 10 will be visited, then 36 will be, 10, then 36 will be visited, then 15 will be visited. So and it should be in the form of a binary, of the form of DLL, right? So we have to convert this tree into a doubly linked list. Okay, we have to convert this tree into a doubly linked list. All right. So and doubly linked list has left will be what? Left will be the previous, I think. The previous and the next pointers, the left and the right pointers in the nodes are previous and next. So the previous will be considered as the left and next will be considered as the right. Okay, so we have to convert this into a doubly linked list. Let's understand how. So 10, let's take this example: 10, 10, 12, 25, 30. 10, 12, 25, 30. Now this is again a very good problem on recursion, right? You have to think recursively here. So 15, 36. 15, 36. Okay, let's understand how. So let's say again we'll follow the same steps, right? Whenever we are building a recursion, how do you know when you can apply a recursion? See, there is no rule of thumb you can understand, but whenever it's like tree like problem, it's involving some tree or some graph like thing, generally what you think about is DFS, or in our case whenever we're using a binary tree, it's recursion, right? So generally that's the way to go, right? So there is no rule of thumb, it's just that you have to understand the question and then decide whether to use recursion or not. So generally for trees and these things we use recursion because we have DFS, which is recursion again, and for other things, for arrays and those things, we might not use recursion, right? So okay, so let's understand this. So let's say we have a 2DLL method, 2DLL method that takes some node, that will take some node and maybe some additional data. We'll identify if we need some additional data, and it will convert the subtree into a doubly linked list. It will convert the subtree to a doubly linked list, and then it will return the updated value. It is also expected to return the updated value as well from itself, right? It is expected to return the updated value from itself. All right. Okay, so what is the first thing when we visit a node? The first node that we should get is the left subtree. So we will first convert the left subtree into a 2DLL. So 2DLL nodes left child, let's call it left. The right will be 2DLL nodes right child. This is the right. Now okay, now what we will return, that is important as well, but here one more thing that is important is how do we combine. So we have this current node, let's say 12, the left child returns 25, the right child returns 30. So we know that the left child will be connected before 12, so the next of 25, the left child will be 12, and like this, right? So or rather the tail node will be there. So probably will return the tail node only. We'll try to return the tail node, and the will return the tail node. Yes, we'll return the tail node only, right? I think that makes more sense to return the tail node. We'll see for different cases. Okay, 12. Now what we return? So for 12, the next will be 30. This. Now what do we return from 12? What do we return from 12? We should not return. Now here the head node will be important, right? Because 12's next will be the head node of 30. So rather we should return two things. We should return two things: tail node and head node. For every recursive call, we should return the tail node as well as the head node. because both of them are important, because tail node is important here. The 25, whatever is in the subtree of 25, let's say 25, 26, 27, some things are there, 25, 26, 27, let's say, whatever is here, the tail of that will be connecting with 12, right? And this will be connecting with the head of the 30 wala series, whatever it is, like let's say 27 or 22, 30, something like that, up to 30. So head is also important, tail is also important. So in this, now this has to return the head and the tail again. So what do we return? The head will be what? Head of this. So head will be the head of left, and the tail of this entire thing, of this entire subtree, what is the tail? The tail will be the tail of the right child, so tail of right. So that is what it will return, right? I hope it doesn't make any sense, so I'll repeat again, right? So see what happens again. Let's say we have a node like this, 10, 20, 30, 40. Just consider this much, okay? What should this return? So when it is constructed, when this is constructed, so let's say this returns the tail and the head. So the tail will be 30, the head will also be 30, right? So let's say 30 is stored in location 100. Let's store the locations here. Let's say this is stored in location 200, this is stored in location 300, this is stored in location 400. So this will return, the tail and the head will be same, 100, 100. Here also the tail and the head will be set 200, 200. This is what it will return as well. Now at 20, what do we want to do? So we have a 30 node. What happens exactly? The next of 30, the next of the tail connects to 20. And this connects to the head of the next one, 40. So now we take the tail from this, so that is 100. The next of 100, we will set it to be 300. And the next of 300 will set the head of the right child. The head of the right child will be 200, right? So this is what we get from here. Now what we will return? We should return the head and the tail. What is the head? Again, head will be this one only, 100, and the tail will be 200. So what exactly is the head? Let's call it head of, let's call the left head. Let's call them like this: left head, left tail, right head, right tail, right? Take a general one. So here, if we take a general linked list, so we have this left linked list where this is the left head, this is the left tail, this is the current node, this is the right subtree, this is the right head, this is the right tail. So this is how they get combined, and this should return the head and tail. So what should be the head? It should be left head. And what should be the tail of the overall thing? Right tail, right? So we'll return left head and right tail, so we'll return 100 and 200. Now for 10, what will this look like? So for 10, this entire thing, 30, 20, 40, 10 will be connecting to this after this. So 10, like this, right? So 10 is connecting to this, so this forms the left part, right? So we return 100, 200, and see the same algorithm applies. The tail, that is 200, the next of 200 becomes 10. So the same algorithm applies here, right? So this will be the logic. So again, we will create a recursive function. We'll create a recursive function. Let's call it 2DLL. It will return two things: head and tail, two pointers, head and tail. So this will be node star. Node star. It will return two pointers, 2DLL, and node star current, the current node we are at. So what we'll do, we'll first find the node star left. We will call 2DLL for the left child, so current of left. Similarly, we'll call this for the right child as well, so node star right, 2DLL for the right child. Then what we'll do is left of tail, that is second, of next equals to the current node, right? Left of second of next is equals to the current node, and also current of previous is equals to the left of second node, that is the tail. And here what we'll do, current of next is equals to right of first, the head node, right of first, and right of first, the node previous to that will be equals to current node, right? Current node. So we are basically what, this is the tail, this is the head, and we are connecting like this. We are connecting like this. So finally we'll return left of first and right of second. So this is what we will do, right? With additional case against nulls, we have to add some additional checks. So this is kind of the code that we want to write. So let's try to write this. All right. So node 2DLL. Now this will not work. I'll try to again go over the entire logic while I write the code. So I think that will help. So pair will take pair node star 2DLL helper, 2DLL, let's call it. And what does it do? It returns the pair head comma tail of the doubly linked list that's generated. So node star current, we are taking node star current, and it will do that, right? So first thing is, if the current is a leaf node, if current of left is equals to null and current of right is equals to null, in that case we will just return a single node containing current and current. That is, this is the head. We'll have a single node. That is the head of the doubly linked list. That is the tail as well of the doubly linked list. So we'll return a single node, current comma current, if this is a child node, right, or leaf node. So this is the condition for leaf node. Else, if let's say the left subtree is not, the right is not there, so current of right is equals to null. In that case, what we'll do is we'll try to generate what is the left subtree. So pair node star left DLL is equals to, we'll call 2DLL for current of left. Now what exactly do we have? We have some set of we have a DLL for the left subtree, let's say 1 3 something like this, 1 2 3, and we want to form a doubly linked list with 4. So 4 should come after this. So it will be like this, that the tail, that is node star tail, is equals to, or left, let's call it left tail. So left tail is equals to left DLL of second, left DLL dot second, and node star left head equals to left DLL dot first. Okay, so left tail of next, it should be, or next means the right. So of right will be equals to the current node, and current of left, that is the previous node, will be equals to left tail, right? And finally what will return? Now we should return the head and the tail pointer. What is the head now? This was the left subtree. 4 is the current node, so the head will be the head of the left subtree, that is the left head. And what is the tail? The tail will be the current node, so left head comma current, that is what we should return. Left head comma current, and current of right we should set it to null, maybe that also works. So current of right equals to null. Okay. Anyways, it's null. It's anyways null, so we don't have to do this. Okay. So can you please summarize? Sina, so what we are doing is we are returning this pair node. This will return. Just imagine 2DLL will actually convert a subtree, the node, the rooted subtree of current, into a doubly linked list. 2DLL will convert the subtree rooted at the subtree current under current into a doubly linked list. So what we are trying to return is, after converting that subtree into a doubly linked list, for a doubly linked list there is a concept of head and tail. So we want to return what is the head and what is the tail for this subtree that we have converted to a doubly linked list, right? So for a leaf node, there is nothing to convert it to, like this is the single node in a doubly linked list, there will be no other node for that part. So for that we are returning current comma current leaf node, right? Because that is the head, that is the tail of the doubly linked list. That is the head, that is the tail of the doubly linked list. I can write on this part. Let's just first understand this. Here I'll write on. So this is just thing that is, there is only one node is there. You are converting it to a doubly linked list. What will be that doubly linked list equivalent to? It will just contain one node. So this is the head, this is the tail. So we are returning current comma current. Okay, this part is clear, the leaf part. Let's come to this part where the right subtree is not there. So in that case, the left subtree is there, right? The left subtree is there. Let's assume that 2DLL works fine and converts a subtree into a doubly linked list, right? So we are calling 2DLL on the left subtree. So let's say on the left subtree, on the left child, there was something like this. The tree was something like this, that let's say the tree was something like this. One, on the left there was let me give some spaces. Okay, 2, 3, something like this, right? 1, 2, 3, something like this. The left subtree is there. 1, 2, 3. Yep. So let's say the left subtree is, for 1 we are computing, the right subtree is not there, the left subtree is 1, 2, 3 like this. So let's say we are calling 2DLL for what? We are calling 2DLL for the left subtree, means 2 and 3. So let's say it is converted into a doubly linked list. How will the doubly linked list look like? 3 and then 2. This is how the doubly linked list looks like till now. 3 and then 2. To this, now this is on the left subtree, right? So to this we will be adding 1 to the end. So now the tail, it returns 2 pointers, right? The head and the tail. Let's say 2, 3, and let's say there was a 4 as well to the right child of this, as a right child of this. So it will be 3, then 4, 3, 4, then 2. Yes, 3, 4, then 2. So it will be 3, 4, 2. So the what is the head? The 3 and tail is 2. So it will return two things. We are assuming that it works correctly. It is converting it to it will convert this subtree to a doubly linked list, and then it will return the head and the tail pointers, that is 3 and 2. We are assuming it returns correctly. So we have to correctly create the doubly linked list here as well. So what do we want to do here? We want to attach to this one as well. Because that is what is required for 2DLL for 1. When we call 2DLL for 1, we assume that this entire thing will be converted to a doubly linked list. So this is already converted to a doubly linked list here. In this line, it is already converted to a doubly linked list. We have the head node and the tail node. The head node and the tail node are given as first and second. So we have separated these two out. Now where will one get attached to? One will get attached to the right side or the next of the tail node of the left subtree. So left tail of right is current, and as it is a doubly linked list, we have to connect back one as well. So one's left child will be, or the previous node will be the tail node of the right child, so left tail. And then we have to return the head and the tail, right? What is the head? The head will be the head that was there for the left subtree. The tail will be the current node, so we'll return left head comma current. So this is for the case for right child is null. Let's create the case for left child is null. So current of left is equals to null. Let's create the case for this. When left child is none, what does that mean? Let's understand this with an example. So we have 1, we have 2 here, we have 3 here. Let's say the left child for this is 4. For 3, the left child is 4. So what we'll do first is we'll first convert the right subtree. We have a right subtree only. We'll convert this right subtree into a doubly linked list. How do we do that? We'll use the recursive function node star right DLL is equals to 2 DLL current of right. Current of right we'll call it with. Now current of right, it has called for this 2, so it will get converted, this 2 3 4 will get converted into a DLL. How will it look like? So node left, right? So first 2 will come in, I believe. 2 left is not there, 2 right. So 2, after that 4 is coming in, after that 3 is coming in, 4 is coming in, 3 is coming in. This is how it looks. And how will 1 get added to this? 1 will be getting added to the front of this. So once next, this is how 1 gets added, right? So let's segregate out first. Node right head equals to right DLL dot first. Node right tail equals to right DLL dot second. Now current of right equals to right head, right? And right head of left equals to current, and we will return current is the new head and the tail will be the right tail. Just see from the example, the new head will be 1 and the tail will be 3, right? So this case is also done. Else if both are present, so we'll convert both of them. So pair node star left DLL equals to 2 DLL current of left, pair node star right DLL 2 DLL current of right. We are converting both of them to DLL. Now we'll extract the left head left tail and the right head right tail out. So let me just copy paste. This will be same. Right head right tail also will be the same thing. So let's just copy and paste. Okay, we have extracted everything out. So what do we have here? We have the left DLL. Let's call that 1 2 3. The right DLL 7 8 9. Let's say 7 8 9, and we have a 5 here. So how will 5 get connected? Again, the left's tails next will be 5. So let's write it down again. Left tail of next of right equals to current of left is equals to left tail. Okay, current of right is equals to right head, right? The right head will be on the right of 5 or the next of 5, and right head of left equals to current. And finally what will return? Will return left head right tail. Will return this. Okay, left head right tail. That is what we will return. So finally here we are to convert this. So we'll return 2DLL for the root node. It returns a pair, will return the head node. So we'll return dot first. So we'll return the first. So let's see. So this is working. Let's submit. Okay, so this is working as well. So this is how we can leverage recursion. During recursion, we'll just assume that the recursive relation is working fine, and we will have to build only for the current condition that we are at. We don't have to worry about how the left DLL is generated, how the right DLL is generated. Just assume the left DLL is generated properly, the right DLL is generated properly. How do we combine these two with the current node? That is what we have to focus on. And if we are doing that correctly, then everything will work fine, right? So we have tackled all the cases and it works fine. So these are the two problems that we wanted to solve today. For your homework, you have to do these questions: intersection of two sorted linked list. So you're given two sorted linked list, you have to intersect them. Delete a node from a BST. We have already we have done insert a node. You have to delete a node from the binary search tree. Root to leaf path sum. So you have to find the path sum from root to leaf, right? And if it is equals to s, you have to prove whether there is a path from root to leaf which is equals to s, and connect nodes at same level. So you are given a tree, you have to connect the nodes that are at the same level. Okay, so these are the problems for your homework, and just think about this. Just try to solve this yourself once. This binary tree to DLL, it's a nice problem. Try to solve it yourself once. If you're not able to, just rewatch the video. I'm pretty sure I've tried explaining clearly, but maybe you haven't thought about this a lot, so that's why it might be a bit difficult for you to understand. So just try to think about it recursively. Once you have done that, and if you're still not able to solve, just come back to this and watch this video again. I'm pretty sure it will help. Yes, just assuming like what are the various cases that can arise. Anyways, thank you guys for joining, and I'll be seeing